Dear students, continuing our lectures on organic reaction mechanism, this is our 28th lecture, and today we will start with the delocalized chemical bonding, and there will be two lectures on delocalized chemical bonding. In the first lecture we will discuss about conjugation in various types of organic compounds. As you know that bonding in most of the compounds can be described by a single structure, but in many of the organic compounds it is not sufficient to explain the properties of those types of compounds on the basis of that single structure. So these types of compounds they contain one or more bonding orbitals that are not restricted to two atoms, but that are spread over three or more atoms. So such type of bonding is said to be delocalized bonding, and the structure of such type of compounds is given by the various types of delocalized structures which are possible for these types of compounds. So if we go by valence bond method, then several possible Lewis structures which are called as canonical forms of different molecules, they can be drawn, and the overall properties of that molecule is taken as average of all the structures which are possible. So for example, in case of benzene, we know benzene exists in these two canonical forms, and this is a resonance hybrid of these two structures. And when this wave equation is solved, and it was found that that A and B, they participate equally, is lower, their energy value is lower than that of A or B alone. So the overall the properties or energy values of benzene can only be explained if we say that this exists as these two canonical structures. And in addition, there is a possibility of these types of additional structures which are called as divorce structures, C, D and E structures, and if these are also considered, the value of A and B is energy value for A and B is still lower than the these three structures, and A and B, they contribute about 39% of the properties of actual molecule, and these three, they contribute about 7.3% of each of these structures. So basically in case of benzene, we can say that benzene can have these two canonical structures. In addition, it has these three more contributing structures, divorce structures, which can also be taken into account for the overall energy values of the benzene molecule. And in case of benzene, the carbon-carbon bond order is 1.463 but not 1.5, which would be the case if only these two they contribute, then the bond order should be 1.5, but because the carbon-carbon bond order is 1.463, that means these three structures, they also contribute towards the overall structure of the benzene molecule. Now if we take the case of different p orbitals present in the benzene molecule, we know if we consider each carbon atom in the benzene ring, there are 6 carbon atoms and 6 hydrogen atoms. So each carbon atom is surrounded by 1 hydrogen and 2 carbon atoms. and these they use sp2 orbitals to form sigma bonds with each other. In all these 12 atoms they are present in one plane, and these p orbitals they overlap through pi bonding, and this type of delocalization of the pi bonds is there. And depending upon the energy of different structures, we can have these types of, this is delocalization throughout the molecule, and this is where one node is present over there, and this is another way of representing where node is present at these places. And by superimposing all these three structures, we can have the pi bonding delocalization in benzene like this. So in other words, the energy of the system is lower than in actual if there is no stabilization due to these canonical structures or Lewis structures. So for example, if we are having say 6 carbon atoms plus 6 hydrogen atoms, the energy for atomization of this is taken into account. In comparison to energy of the benzene system, there is a difference of 1323 kilocalories per mole of energy. So that means if benzene is to be atomized to give us 6 atoms of carbon and 6 atoms of hydrogen, then this much of energy is required. So similarly, if 6 carbon atoms and 6 hydrogen atoms they combine to give us benzene, that means this much of energy will be released during the system. And if we are having either structure A or structure B, then conversion of this into structure A or B gives requires 1289 kilocalories per mole of energy. So basically that means the difference between this and this will give us the resonance energy, that is the difference in energy between actual molecule and the Lewis structure of the lowest energy. This is called as resonance energy. So we know that either structure A or structure B, they have similar energy, and they are the Lewis structures of lowest energy. So difference between the energy of the actual benzene molecule and these two, any of these two, is called as resonance energy. So if we make the difference, the resonance energy in case of benzene comes out to be 34 kilocalories per mole. Then the molecules which exhibit delocalization, they can be discussed under 4 types of molecules. First type of molecules is having those molecules which are having either double bond or triple bonds in their conjugation. Then second category is the molecules having double or triple bond in conjugation with a p orbital on an adjacent atom. And third one is pi-allyl or other eta complexes which can show delocalization of energy. And then delocalization can also come through a phenomenon called as hyperconjugation. Now first category is the molecules where we are having double or triple bonds in conjugation. We have seen the case of benzene where we were having double bonded in a cyclic molecule, but this conjugation can also exist in acyclic molecules such as butadiene. So if you see this molecule butadiene, if this pi bond shifts to this position and this pi bond along with its electron pair shifts to this carbon, that means this carbon will be having positive charge, this will have double bond, and this will be having negative charge. So this type of resonating structure is possible for butadiene. Similarly, if this bond goes to this place and this bond goes to this place, then this carbon will have positive charge and this carbon will have negative charge. So these are the three resonating structures which are possible for this 1,3-butadiene. And if we go by a molecular orbital picture of 1,3-butadiene, the overlap of 4 orbitals, these 4 orbitals in case of 1,3-butadiene can give rise to 2 bonding orbitals which will contain the 4 electrons which are present, these 4 pi electrons, and 2 vacant anti-bonding orbitals. And we can see over here that if all the nodes having negative and positive, they are on the same side, there will be the perfect overlap between the pi electrons, 4 pi electrons which are present in the molecule. But these 4 orbitals they can have different energy because of the fact that the overlap may be perfect or it may be different. So for example, when all the 4 nodes having negative and positive, then energy of the system will be alpha plus 1.618 beta. Similarly, if there is one node in the bonding orbital, these are the 2 bonding orbitals. So one node is present, then the energy of the system will be alpha plus 0.618 beta. Similarly, then this orbital is of lowest energy, then this will be the second one, then this will be higher than this, and this will be higher than this. So as we go from lowest energy to highest energy, the number of nodes increase by 1 from the next lowest energy level. So this is lowest in energy, next one will have 1 node, and next one will have 2 nodes, and next one will have 3 nodes. So similarly, the energy of the system will be defined like this. The energy of the third orbital with 2 nodes will be alpha minus 0.618 beta, whereas fourth one will be alpha minus 1.618 beta. And if we combine the energy of 2 isolated double bonds, that will be equal to 4 alpha plus 4 beta. And whereas the total energy of 2 occupied orbitals in case of 1,3-butadiene is 4 alpha plus 4.472 beta, and basically that means the resonance energy is 4 alpha plus 4 beta is energy of the isolated double bonds, and resonance, that mean is by 0.472 beta is the resonance energy which can be calculated on the basis of molecular orbital picture of the 1,3-butadiene. Similarly, the molecules where double or triple bond is in conjugation with p orbital of an adjacent atom, and this is the example, then there will be 3 orbitals and conjugation will be with the third orbital where a p empty orbital is present. And in this case there can be 3 combinations, either bonding or non-bonding or anti-bonding type of orbital overlap may be there. And the non-bonding orbital will be having energy equal to the atomic orbital. So this is a 0 bonding energy, and central atom does not participate in the non-bonding orbital. And in these types of cases where there is a p orbital on the adjacent atom, we can have different examples. The most common example is that of vinyl chloride, and this vinyl chloride, because this chlorine atom can share a pair of electrons with it, this can acquire positive charge and this carbon can acquire negative charge, and we can have these types of these are the p orbitals present on these 2 carbons, and this one is the filled orbitals of halogen, and this is the empty orbital of the halogen. So original p orbital may contain 2, 1 or no electrons. So depending upon the type of example which we take, there can be 2 electrons present in the adjacent p orbital, or 1 electron, or it may have no electrons. So depending upon this, the original double bond contributes either 2 electrons, depending upon the fact that electron accompanied by new orbitals will be 4 if 2 in the original and 2 they are contained by the p orbitals, there will be 4. If this is having 1 and original double bond contributes 2, then total will be 3. And if it contributes original p orbital having none electron, that means only double bond will contribute, that total will be only 2 electron. So as I have told you, in case of vinyl chloride, the p orbital of chlorine atom is filled, and that is why it still overlaps with the double bond by contributing that 2 electrons, and total there are 4 electrons which can occupy the 2 molecular orbitals of lowest energy, and these are the 2 canonical forms of vinyl chloride which can be written. Then another example is carbonate anion. So here we can see that this double bond, if goes to this place to form a double bond, carbon oxygen double bond, then this will go to this place, and we can have these 3 canonical structures for the carbonate anion. So it has an unshared pair that is directly attached to a multiple bond, and atoms can show this type of delocalization. Similarly, allylic carbanion or allylic carbocations, they also show similar type of delocalization as we have seen in case of this vinyl chloride. Then third type of molecules, they are pi allyl and other eta complexes. These types of molecules, they are generally organometallics, where transition metal is having delocalized cations which are stabilized by donating electrons to the metal. So we can say that we are having carbon metal bond, such as say methyl ferrite is the example. Here the carbon donates 1 electron with the metal, and this is considered to be 1 electron donor. So carbon is 1 electron donor in this case, and such type of complex will be called as eta 1 complex. And with a pi bond, for example, in case of ethylene, we know there is a double bond, and both the electrons, they can be donated to the metal to form a complex. For example, in case of Wilkinson catalyst, this one, if we react this with alkene and hydrogen gas, we know that these 2 electrons of the alkenes, they can be donated to this rhodium metal to form this type of metal alkene complex, which can ultimately lead to the reduction of this alkene to alkanes. So this here this is a 2 electron donor. Alkene is acting as 2 electron donor, the pi bond of this alkene. And here the depending upon the number of electrons which can be donated, the classification of these types of complexes is done. If there is 1 electron donor, then we call it as eta 1 complexes. If 2 electron donors, we call these as eta 2 complexes. If 3 electron donors, eta 3 complexes, and so on, depending upon that how many electrons, they are donated by the pi electrons to the metals. So for example, if in this case we take the hydrogen atom, in this case, or halogen ligand, they are eta 1 ligands, because they can donate 1 electron to these complexes. Similarly, the phosphine, triphenyl phosphine, in case of A or this B, they are called as N2 ligands, because they can donate a pair of electrons. So we can see over here, out of these 3 triphenyl phosphines, 1 triphenyl phosphine is eliminated when alkene adds to this metal complex to form this metal complex, and we know that the alkene is a 2 electron donor, and phosphine which is removed is also a 2 electron donor. And then next is ligands, some more example of such type of eta ligands, and according to this, for example, carbonyl group, in case of this molecule or this molecule, in both the cases, and or an ether or thioether, all these they can donate 2 electrons, and that is why these are called as eta 2 ligands. Whereas hydrocarbons like alkyls, for example here, they can donate 1 electron, or alkyl or aryl, they can donate 1 electron to the metal, hence they are eta 1 type of ligands. Then, as we have seen in the previous slide, alkenes or carbenes, they are eta 2, pi allyl, they are eta 3, because they can donate 3 electrons. Conjugated diene such as butadiene, they can donate 4 electrons, hence eta 5. Cyclopentadienyl, they can donate 5, so they are eta 5 ligands for these types of complexes. And other typical examples, they include chromium hexacarbonyl, this one. Here we are having 6 eta 2 CO ligands which are attached. Then in case of D, we are having 3 carbonyl eta 2 ligands, and one is benzene ring which is attached to this. And here in the next example, this one, tetra case triphenyl phosphino palladium 0, here we are having 4 phosphine ligands which each can donate 2 electrons, hence eta 2 phosphine ligands, they are there. Then next is hyperconjugation. Hyperconjugation is donation of electron density from a beta hydrogen of a carbon or a carbon-carbon bond into an unoccupied p orbital of a carbocation. For example, like this, if this is the carbon hydrogen sigma bond, and if this electron density is transferred to the vacant or 2p orbital of this carbon of the carbocation, then such type of transfer is called as hyperconjugation. And more the number of hyperconjugative structures possible for a molecule, higher will be the stability of that molecule. So delocalization is much more in case of tertiary butyl cation as compared to isopropyl cation or ethyl cation or methyl cation. So as we move from here there is no hyperconjugation, whereas in case of ethyl cation there are 4 structures which are possible, which can give you hyperconjugation. So here only one structure is there, here 4 hyperconjugative structures are possible. In case of isopropyl cation there are 7 hyperconjugative structures which are possible. whereas in case of tertiary butyl there are 10 hyperconjugative structures which are possible. So higher the number of hyperconjugative structures possible, higher is the stability of the cation. So this is how hyperconjugation affects the stability of different kinds of molecules. The next is cross conjugation. Cross conjugation is different from conjugated compounds. In case of cross conjugated compounds, there are three groups which are present, and two of these three groups, they are not conjugated with each other. So although each is conjugated with the third one. For example, we can see over here. So here we are having this bond and this bond, but this is in conjugation with this bond but not with this bond directly. Then this bond is in conjugation with this bond but not with this bond directly. So this type of conjugation is called as cross conjugation. Similarly, in this molecule, this bond can undergo delocalization with this this part of the molecule, that is this double bond, but not directly with this double bond, whereas this double bond can undergo delocalization with this double bond and not with this double bond directly. So such type of conjugation is called as cross conjugation. So these are the three examples of cross conjugation. Similarly, in the third example you can see the divinyl ether, the two lone pairs present on oxygen, they can undergo delocalization with either of the double bond, but both the double bonds, they are not in conjugation with each other. So this type of phenomenon is called as cross conjugation. So likewise, depending upon the type of overlap, the stability of the different molecules is there. Then some more examples of cross conjugation. Here in this molecule you can see that the cross conjugated bond is 0.01 angstrom longer than in the normal circumstances because of the cross conjugation. So this bond is in conjugation with this bond but not with this bond, triple bond, and this triple bond is in conjugation with this double bond but not with this double bond directly. So this is an example of cross conjugation. Similarly, one more phenomenon is there which is called as homo conjugation, and homo conjugation is related to cross conjugation in a way that CC units, the cross conjugated units, they are in close proximity but not conjugated with one another. So here in this molecule, this spiro-4,4 nona-tetraene, so these two bonds, they are in conjugation with each other, and these two bonds, they are in conjugation with each other, but these are not in conjugation with the second ring. So such type of conjugation is called as homo conjugation. So here highest occupied molecular orbital is raised relative to the other cyclopentadiene, whereas the lowest unoccupied molecular orbital is not affected by this type of rotation of this ring. And then this is the third example where the bond length for these molecules becomes distorted due to the electronic interaction between this unsaturated bicyclic moiety and this cyclopropyl moiety, and because of this there is a conjugation between these two bonds through this cyclopropyl moiety. Then last is p pi d pi bonding. and this p pi d pi bonding takes place in different types of ylides of phosphorus, nitrogen or sulfur molecules. So here we can say that there is another type of double bond which is generally present in sulfur and phosphorus. For example, in this molecule H2SO3, so we are having this sulfur oxygen double bond, and this acquires this type of resonance because sulfur can acquire a positive charge and oxygen is more electronegative, so it can acquire a negative charge. So likewise, the p orbital from oxygen with an empty d orbitals from the sulfur, they can undergo overlap, and such type of overlap is called as p pi d pi orbital, and this type of bonding is called as p pi d pi bonding. And similarly, in case of phosphine oxide, we can have this type of overlapping between phosphorus and oxygen. In case of sulfoxides, we can have this type of resonating structures. In case of sulfones, we can have this type of resonating structures. So here in all these cases, the molecules, the sulfones or sulfoxides or hypophosphorus acid or phosphine oxide, they can be represented by two canonical structures, and these structures, they can be formed because of p pi d pi bonding. Then the sulfur and phosphorus ylides, these are important entities in case of organic synthesis. Here these types of molecules where this oxygen is replaced by this type of methylenic carbon sulfur double bond, and these ylides, they may be defined as compounds in which positively charged atom is from group 15 or 16 of the periodic table, that is either sulfur or phosphorus or nitrogen is there. Then they can donate electrons to a carbon which is carrying an unshared pair of electron is present on the carbon. So the molecules which can be converted into these types of dianionic structures, they are called as ylides. If the molecule, if the atom involved is sulfur, we call these as sulfur ylides. If the atom involved is phosphorus, phosphorus ylides, or nitrogen as nitrogen ylides. So due to this p pi d pi bonding, the two canonical structures can be written for sulfur and phosphorus, and only one canonical structure for nitrogen ylides. The phosphorus ylides, they are more stable than nitrogen ylides, and sulfur ylides, they also have low stability, and these are the most stable ylides which are reported for in the organic synthesis. So this is the reference. Most of the lecture is from Jerry March 6th edition, Organic Reaction Mechanism. Thank you very much.